Okay, one more video for week 1 of vibrations. Boy, this has been ambition. All right, so here's another rigid body lumped mass example as taken from Dr. Bob's notes to accompany this course. He was kind enough to share them with me. The static deflection of the spring in the position shown is 0.55 inches. The uniform bar weighs 5 pounds, and the mass at the end is 3 pounds. The dimensions are 16 inches and 8 inches. Determine, did they ever tell us? Oh yeah, I know why. Okay, so there's a little clever thing we have to do here. Determine the natural frequency in hertz of the system. So for one thing we don't know is we don't know the K. But we do know that the thing is horizontal right now in this position shown. Right? So it has static deflection. So we can figure out what the deflection of the thing must be by using statics. So we'll start out with some statics of this. And draw our free body diagram. Here. Mix the colors up a little bit. You got this. Oops, I didn't change it. And this. So how did I draw that? I want I should have called MC. MC G. And then this should be M A B C G. I should have left myself some room for, I'll do it right here. I know that the FS, that's the spring, and then we have reactions right here. So here we go. RAY, RAX, they're basically going to be, RAX is going to be 0. So you know, the sum of the moments about A, because we don't care about the reaction there. And we'll say that we have negative MABC times, we had to go in the middle of it. That's always annoying. XAB plus XBC over 2. Right? Because we want to get right in the center of this piece, so we have to get halfway along there. Well, need to be a G. I put my G. We can just put the weight, right? They gave us the weight. They gave us the weight of the thing. So I'm gonna go. I should have written WABC. All right. So there you go. Right in the middle. Plus. Right. So because that was, it's going clockwise. This is going to go counterclockwise. So it's going to go FS times XAB. Now we need the weight of the ball, and that's going clockwise. So we get weight of C, and that should be times XAB plus XBC equals 0. All right, so you think your way through that. And so I said the F of the spring, when it's static, is going to be equal to, I guess I decided to work it out here. It's going to be 5 times, let's say, okay, I guess 16 plus 8 is 24, divided by 12 is 2. So it's going to be 2 divided by 2, right? So that was the bar right here. Divided by 2, right? Because we don't want to do everything in feet. Plus the ball was 3, and this is also the XAB and XBC added together and divided by 12, 2. And then we want to divide by XAB. which was 16 divided by 12, which is 1.3333. And so that equals 8.250 pounds. All right, so if we want to find the okay, so that's the force, and oh, it's the position is okay. So the deflection, static deflection, right? So we want to have K is going to be F over del, which is going to be Fs over del. So we have 8.250 divided by 0.55, but divided by 12 because we were given it in inches. So, did I do it wrong? No, I'm fine. I get 180 pounds per foot. All right, so that's part one there, really. We want the natural frequency of the system, though, so we need to draw and create an equation of motion for this thing. So start out with an FBD and IBD. So remind yourself what it looks like, this thing. Okay, we need to make a oh man, I got the wrong answer on this thing. Oh gosh. All right, so I'm going to go through it, but I'm going to recognize that there's a numerical mistake somewhere along the way. So just be aware. Okay. So we have take this thing at an angle. Set equal to each other. Is the rod? Yeah, the rod sure enough has a thing. So ABC, WC. If it's in this position, this force is coming upwards, Fs, and reactions are R, A, Y, and R, A, X. Over here on the other side, we can go this one, I, about A, and alpha. We'll just go ahead and call it theta double dot, right? Why not? All right. Anything else on this? No. Except maybe getting the angle straight. And oops. Here's my theta. All right. So some of the moments about A is equal IA theta double dot. Did I find I anywhere? That's a good question. I do know I, but where did I calculate it? I think maybe I ignored it. Looking for it. Where'd you calculate it? Where'd it go? Oh, there it is. Okay. IA is equal to the I of the rod, boom, plus the mass of the rod times the distance of the rod it has to move to A squared, plus, we're going to assume that this sphere doesn't really have much, isn't large enough to have a significant mass moment inertia, but we do need to move it, of the ball times the distance that the ball has to move squared. So that's my maybe where I'm making a mistake, right? It didn't tell me the diameter of the thing, so this will be 1/12. 1/12. Rod is 5 pounds over 32.2. Its length is 2 feet long squared plus, but we have to move it. So we're going to move, it's going to be 5 over 32.2. And the distance we have to move it is 1 from its mid, because that's the center of the thing. It's going to be squared, but it don't matter because it's 1 plus the mass of the ball, which is 32.2, but it's got to be moved 2 feet, and that's squared. So I end up getting 0.5797, and these are slug feet squared. And then I can start with this stuff over here. So we got the weight of the piece. By the way, these weights end up canceling out because of the statics. So if we did the static and we subtracted the thing out because it's in equilibrium right here, we would, if we had plugged in all of this stuff and set what the static spring was going to be, that would have plugged all of the nonsense in. So I kind of should draw that out, but I'm feeling lazy. But anyway, let's see. Let's do it anyway. WABC times X. Yeah, it's going to be in line with it, so we don't have to actually worry. So it's XAB plus XBC over 2, right? And that's going clockwise, so it's negative, and the length of the thing is going to actually be, yeah, no, that is the length of the thing. Yeah, okay, so there you go, that's the moment. We're going to have plus the Fs, which is, Fs is going to be equal to the K times del, which is going to be K times XAB times theta, right? Because it's going to be the angle. That's the amount of distance it has traveled right there times that distance. Okay, so that's going to be K XAB theta, but it's squared, right? Remember, this is the small distance approximation note. And then we're going to keep going here with the minus WC, and that's going to be XAB plus XBC, and that's everybody on the left-hand side. It's going to be equal to, and I decided to make it counterclockwise, so it's positive. So I'm going to have IA times theta double dot. So I'm hypothesizing that if were I to also include the if static was also included, W's go away. Now, how do I know that? Well, because the W's are constants right here, right? They don't have a theta in front of them, so they're not going to be related to the dynamics of the situation. Is another way that we can put it into that. So as we're drawing this thing up, we could say that IA theta double dot, and I get a negative right here, which just means that I should have probably chosen a different direction onto the thing. It's pretty common. You know that they're going to be positive, so it doesn't really matter. I've seen it done other ways where you take the phase of the thing and fix it. But in all honesty, it's all the same stuff. Did I do this wrong? No, I think I'm okay. Theta equals 0. So we're going to go, our equation of motion is going to be theta double dot plus k xab squared over ia theta equals 0. And what are we asked here? We want to find the natural frequency. So we're going to get Fn is equal to 1 over 2 pi square root of k xab squared over ia and 1 over 2 pi square root of k we established was 180 pounds per foot. Xab was 16 divided by 12, or 1.333 feet squared, divided by 0.5797 slug feet squared. And this turns out to be 3.738 hertz. But Dr. Bob's answer was 3.92 hertz. So we had y. Why is that my? So here's my answer. But they're close to each other. Dr. Bob's answer. We can, I'll go ask him, maybe. And he can go, you need to go back to college, son. You don't know what you're doing. Like, yeah, I agree. But I got tenure, so too late. Talk to you soon.